All right, so this is Chapter 7, Section 3, Logarithmic Functions as Inverses. Our learning objective is to write and evaluate logarithmic expressions and to graph logarithmic expressions. Our essential understanding is that when we have an exponential function, y equals b to the x, it's 1 to 1. So the inverse, and remember, to find an inverse, you switch the x and the y and solve for y. X equals b to the y is a function. To express y as a function of x, for the inverse, we write y equals log base b of x. Okay, so here's what I want you to write. All right, a logarithm base b, I want you to definitely write down logarithm, base b of a positive number x satisfies the following definition. So I want you to write this guy here. For b greater than 0 and b not equal to 1, log sub b of x equals y. I don't want you to have the if and only if part. And b to the y equals x. Log sub b, so that means base b, log base b of x equals y. B to the y equals x. Log base b of x is how we read that term. So the logarithm y is the exponent to which b must be raised to get x. The exponent y in the expression b to the y is the logarithm in the equation log base b of x equals y. The base b in b to the y and the base b in log b of x are the same. In both, b can't equal 1 and b has to be greater than 0. Since b can't equal 1 and b is greater than 0, we know that the result b to the y is greater than 0. Since b to the y equals x, then x is also greater than 0. So log, and then let's highlight that too. Here we are. Log base b of x is defined only for x greater than 0. Because y equals b to the x and y equals log base b of x are inverse function, their compositions map number a to itself. In other words, if you have base b and in its exponent, log base b of a, it's going to be equal to a. And if you have log base b of b to the a power, it's equal to a. So I want you to write those down as well. This here and this here. Let me pause it so we can. I'm going to write it down on the board as well. Okay, so we are going to A, B, and C transform these equations into logarithmic forms. So if I want, it's going to have b to the y equals x. This is exponential form. If I want to transform it, whatever my base is, it's going to go down as a subscript to the log. Whatever's on the other side of the equal sign, that's going to go right next to the log. And then whatever was in the exponent is going to go out after the equal sign. So in this case, 6 is b. 2 is y, and x is 36. So putting that into logarithmic form, we're going to go log base 6 of 36 is equal to 2. Go ahead and try B on your own. The base is 2/3, the exponent is 3, and the y value is 8/27. Awesome. And then the last one would be log base 3. The x is x0. It's 1. Nope. 1 equals 0. X is 1, y is 0. One thing I'm going to have you guys add to this is 36 we can write as base what to the 1? 36 is a perfect square, right? It's 6 squared. This is an example of what I had you guys write down, where log base b of b to the a equals a. I just wanted to point out that's where this information applies. The same can be said of this guy here, log base 2/3 of (8/27). Is that 2/3 to the 3rd power? Yes, it is. And so you can see that the log and the base cancel each other out, so I'm just left with 2. The log and the base cancel each other out. I'm left with 3. I don't have the same, although I could write this as 3 to the 0. I could write 1 as 3 to the 0, but I'm not going to. Okay, so we now can use logarithmic properties. We can use this setup to find the value of each logarithm. So if I was going to say the log of base 5 of 125 equals what? So let's shuffle it around. Convert it back to exponents. So 5 is the base, y is the exponent, and 125 is the answer. So 5 to the what power is 125? No, it's not squared, right? So 5 times 5 is 25 times 5. So y would have to equal 3. So the log base 5 of 125 is 3. Let's apply the same thing here. We are going to have log base 4 of 32 is going to be equal to what? Let's shuffle it around. Our base is 4, our exponent is y, and our answer is 32. Problem is, 4 times 4 is 16, and 16 times 4 is 64. There is no power of 4 that's going to give us 32. However, you're smart. Say that to yourself for a moment now. I am smart. Mrs. Albagarth had us write down all of a chart with perfect cubes and perfect squares and even perfect fifth powers. So I know that 4 is the same as 2 squared. And we know 32 is 2 to the 5th. So 2 to the 2y equals 2 to the 5th. Same base. We know that 2y has to equal 5, or y has to equal 5 halves. What? Okay, so if you don't know where your chart is, or it's packed away in the previous chapter, make sure you have it handy because we're going to use it for here as well. So get that chart out. Okay. Last one in this section. Log base 64. So I'm going to rewrite this as base 64. To what power equals 1 over 32? That sounds crazy. I give up. Just kidding. There is no give up. So we are smart enough to know that 64 is related to base 2. Two to the what is 64? I know 2 to the 5th is 32. So that's right, 2 to the 6th has to be 64 because 32 times 2 is 64. 1 over 32 is the same as 1 over 2 to the 5th. This is also equal to 2 to the negative 5. Remember, when I apply a negative in the exponent, it doesn't mean that my value is negative. It means that I have a fraction. So we're working our way backward. 1 over 2 to the 5th is 2 to the negative 5th. So in this case, I have 2 base 6y is equal to 2 to the negative 5th, meaning so if our bases are the same, our exponents have to be equal as well. So y has to equal negative 5, 6. Not because our values are negative, but because we have a fraction. So I have good news and I have bad news. There are only 2 logarithms that your calculator deals with. One is a common logarithm, one is a natural logarithm. Your calculator does not deal with any other bases except those 2. So we're going to talk real quick about a common logarithm. A common logarithm has a base 10. We can write a common log as log base 10. Most of the time, we leave off the 10 and we just write log x. So if you don't see a base on the logarithm, it has base 10. Don't write this down, but we're going to talk about it. Many measurements of physical phenomena have such a wide range of values that the reported measurements are logarithms or exponents of the values, not the values themselves. When you use logarithm of a quantity instead of the quantity, you are using a logarithmic scale. The Richter scale is a logarithmic scale. It gives logarithmic measurements of earthquake magnitude. So here is our friend, the Richter scale. I do want you to write this formula down. Log I1 over I2 equals M1 minus M2. It compares the intensity level, where I is the intensity level determined by a seismograph, and M is the magnitude. We are going to use this formula to solve problems, so it's important to write this down. So let's see how we can use this. In 1995, an earthquake in Mexico registered 8 on the Richter scale. In 2001, an earthquake of magnitude 6.8 shook Washington State. How many times more intense was the 95 earthquake than the 2001 earthquake? So we're going to take the log So the log of the first intensity over the second intensity is equal to M1, so the magnitude of the first one is 8.0, minus M2, which is 6.8. Thankfully we can do that math. 8 minus 6.8 is 1.2. So now we have to use what we know about log. So log, the base on this one, since I don't have anything written, is base 10 of I1 over I2 equals 1.2. We look at how that's log base B of x equals y, where b is the base, y is the exponent, and x equals what's on the other side. So we're going to shuffle this around, and we're going to say we got I1 over I2 is the x. The base is 10. And the exponent is 1.2. So now we just do that calculator operation. Where we go 10 to the 1.2. 15.8. Let's go ahead and round it to the nearest whole number. So we say the intensity is about 16 times greater. So 15.8 rounds to 16. All right, so now we get to the graphing part of our learning objective. A logarithmic function is the inverse of an exponential function. The graph shows y equals 10 to the x. So that's this guy right here, y equals 10 to the x. And its inverse, y equals log of x. Remember, it's symmetric along the line y equals x. 0, 1, and 1, 10 are on the graph of y equals 10 to the x, and 1, 0, so flip the x and the y, and 10, 1 are on the graph of y equals log x. Remember that graphs of inverse functions are reflections across the line y equals x. You can graph y equal log base b of x as the inverse of y equals b to the x. So let's go ahead and do that. What is the graph of y equals log base 4 of x? Describe the domain, range, and y-intercept. Okay, so let's convert this back to its exponential form. Our base is b. Our exponent is y. when you convert it back, the x and the y need to switch, because what is an inverse? We switch the x and the y. So that's why this is not going to be 4y. We're going to graph actually 4x to the x power equals y. So to graph this, I'm going to pull my important points. I'm going to pull where I'm at when y equals 0 and x equals 0 and y equals 1. So when x equals 0, 4 to the 0 is 1. Anything to the 0 power is 1. 4 to the first power is 4, and just for fun, 4 squared is 16. So when I go to graph this, we have, goes through 0, 1, and then when it's -1, it's 1, 4. So it's kind of like this guy here. And then when we are power 1, we're up 4. 1, 2, 3, 4. And then we're power 2, we're like up at 16. So our inverse is going to be the same coordinates, just switched. So when x is equal to 1, y is equal to 0. When x is equal to 4, y is equal to 1. And when x is equal to 16, y is equal to 2. So we put that on our graph. Over 1 up 0. Over 4 up 1. And we have the inverse. All right, it wants us to describe the domain, range, y-intercept, and asymptotes. Okay, so let's put those all together. The domain of the graph, of the red graph. So what x values can we not put into this function? Do you want to make me go back to the first slide, or can you guys just say, you're going to make me go back to the first? Okay, we're going back to the first slide. Here we go, on a journey. So the log base b of x is defined only for x greater than 0. So we can only have x greater than 0. So our domain is x greater than 0. Our range, so let's look at our outputs. When I am down here, I can input negative numbers all day into my inverse function. So remember, the domain of the inverse is the range of its buddy. So so I can input any number I want here. There's no restriction on what exponent I can put in. So the range is all real numbers. The y-intercept, so when does this cross the y-axis? Never. So there is no y-intercept. And you look, its inverse never crosses the x-axis. So it makes sense that its buddy inverse would never cross the y, because those are just switched. So the y-intercept is none, and then the asymptotes. So I have the line y equals 0 is an asymptote. We can get really close, smaller and smaller, but we can never actually get to that. Since I have no y-intercept, I can't get close to y equals 0, so my asymptote is y equals 0. let's take a look at logarithmic functions as a whole and apply what we know to translations to the logarithmic function. So if your parent function is y equals log base b of x, in order to stretch, compress, or reflect, we are going to fuss with a multiple of that function. So any coefficient of that function, whatever's in front of the log, is either going to stretch if it's greater than 1, compress if it's between 0 and 1, or reflect if it's negative, and or reflect. If we want to move it horizontally or vertically, we take, and inside the logarithm is how we move it left or right. So it's log base b of x minus h. If you have plus inside, that moves it left. If you have minus inside, that moves it right. And then the k moves it up or down. If k is positive, it goes up. If k is negative, it goes down. Putting all these together in one amazing function that we're going to compare all these other functions to. Y equals a log base b of x minus h plus k. Okay, so we are going to take this guy right here, and we're going to compare them to our function here and see how does it compare to the parent function. So this is a graph that is shifted because I have a negative inside there. It's going to be shifted, right? Three units. And then this guy is the k. It's going to be shifted because it's positive. It's going to go up 4 units. It doesn't have a coefficient out in front of the logarithm, so there is no stretch, compress, or reflection. Okay, let's look at our next guy. He's covering the stretch for us. We have no values inside the logarithm or outside the logarithm being added, so there is no translation right, left, up, or down. We do have this coefficient. Since the absolute value of 5 is greater than 0, we are going to have a stretch by a factor of 5. Because he is positive, there is no reflection. And that's it for today's lesson.